So the first few sections, sections 1.1 through 1.3, we started working with the concept of limits and continuity. The big reason where we teach the concept of limit is because it's kind of the foundation of calculus. And very specifically, the next two sections, sections 1.4 and 1.5, are kind of the foundation for all of chapter 2, all of chapter 3, and all of chapter 4. And we only cover 5 chapters. So these are important sections. We start off reviewing some algebra, and then we add a limit to the algebra to turn it into calculus. And let me just kind of jump into the algebra part of this, and then in a little bit we'll tack on the limit to turn the algebra into calculus, and I'll try to talk about, why this is important. So on the screen right now, I wrote a definition for average rate of change, which is something I calculate in Math 114 and something I calculate in Math 151, college algebra, prep, and college algebra. So you very well might be familiar with average rate of change. If you're anything like I was when I was a student, I learned stuff and got A's in all my math classes, but quite honestly, by the time the class ended, I don't know what I remembered, but it was really minimal what I remembered. And so every time I learned something, it's like it's new to me. So I'm assuming this is new to some of you. So the average rate of a change of a function over an interval is given by this equation. And this equation turns out just to be an equation for slope written in function notation with slightly different variables. But the average rate of change is just the slope of a straight line that connects 2 points on the graph of a function. And the average rate of change is a measure of how the function changes per unit on average over that interval. That's a wretched definition. This is my lack of English ability. But really, if I just think of the average rate of change as the slope of a straight line connecting 2 points, that's going to be enough. As we get into word problems, maybe I'll talk more about what I tried to type here that's really, kind of not written so well for anybody that's, takes pride in their English. So let me just review some algebra. So I want to find the average rate of change for a function. So the instructions for this example say, find the average rate of change over this function, f of x equals negative 2x squared plus 4x minus 5, over the given interval, x equal to 1 to x equal to 3. Sketch a graph to model your answer. You can steal a graph from your calculator and copy it to your paper just because this is not a graphing section per se. It's nice to see the graph to understand what's going on, but our graphs don't need to be so accurate. So how do I find an average rate of change? An average rate of a change is really just the slope of a line that connects 2 points. And what I've given here is the tools to get those points. The two values that are given in the problem that say x equal to 1 and x equal to 3, those are the x coordinates of the points that I need for my average rate of change. If I have a function and an x value, well, I can get y's all day. I get the y's by taking the x value and plugging it into the function. So this is what I started to do. I give you two x values, which is kind of half of 2 points. The average rate of change is just the slope of a line that connects 2 points. For each x, I need to get its corresponding y. I get the y's by taking the value for x and plug it into each x in the function and do the algebra. So this I just did on my calculator. But you plug 1 in for x and do the algebra on your calculator, you're going to get negative 3. If I wanted to, I could just pull out my calculator and do negative 2 times 1 squared plus 4 times 1 minus 5. And I'd get that negative 3. So that's all I did, is I just press buttons on my calculator, which I don't care to show here. When I plug 3 in, changing that x, and that x to 3, and do the algebra, I get negative 11. So I'm trying to find the average rate of change between the point 1, negative 3 and the point 3, negative 11. And because average rate of change is just the slope, I'm going to subtract the y's in the numerator, the y coordinate of the second point minus the y coordinate of the first point in the numerator of the fraction. And then I'm going to subtract the x's in the denominator. So my average rate of change, is simply the slope of the line that connects the 2 points that are implied by the instructions. The y's get subtracted in the numerator, which is -11 minus -3. The x's get subtracted in the denominator, which is 3 minus 1. In the numerator, the double negative with the 3 turns positive. In the denominator, 3 minus 1 is 2. Now in the numerator, the numbers have opposite signs, so I subtract and take the sign of the larger. And I get the average rate of change is -4. So it's simply not particularly hard to do. Let me show you this visually and maybe talk about what this line is visually. So I graph the function -2x squared plus 4x minus 5 using Desmos, which is a program I loved. And I plotted the point 1, -3 and the point 3, -11. The slope of this line is the average rate of change. The slope of this line is m equal to -8. And this is a special kind of line. When you have a line that connects 2 points on the graph of a function, when it connects any 2 points, this line that I drew in here is called a secant line. So if I wanted to use my calculator to sketch a graph, I know that this thing's going to be a parabola. On my calculator, if I wanted to get a graph that looks like this, I might just enter the function -2x squared plus 4x minus 5 on my calculator. And if I just say graph what it looks like. That's good enough. There's a graph of the function. And now I want to add the points. So what I'm going to do is figure out where the point +1, -3 is by going second calc, hitting enter on value, typing the number 1, and it shows me there's the point 1, -3. And now let me type in 3 and hit enter. And there, it can't show me where the point 3, -11 is because it's off the screen. I need to make my window go down a little bit. My y's need to go lower to see 3, -11. And now if I do second calc value, it's going to regraph it to the new window. And when I type in 3, it shows me the point 3, -11. So I can borrow each of those points from my calculator and just connect them. And so this is a visual representation of the average rate of change. The average rate of change is the slope of a line that connects 2 points. The name of a slope of a line that connects 2 points is called a secant line. So this is kind of the second bit of what I typed up. This right here, the average rate of change, is just the slope of the straight line connecting 2 points on the graph of a function. This mangled English, let me try to show you in a word problem what an average rate of change is and how we can attach units to the average rate of change. Doing a very simple example. So at 10 a.m., a car's odometer read 10,300 miles. At noon, that same car's odometer read 10,420 miles. What is the car's average rate of change measured in miles per hour? Well, I don't have a function to deal with, but the average rate of change is just the slope of a line that connects 2 points. I, in a word type problem, have to decide where the x's and the y's need to be. And this completely tells me what needs to be x's and what needs to be y's. It gives me the units for the average rate of change. And we realize that average rate of change is a fraction that has the y's in the numerator and the x in the denominator. And this fraction, it needs to reduce to miles per hour. And how can I create a fraction that when I reduce it, I get miles per hour for my units? Well, very specifically, the units in the numerator need to be miles, and the denominator needs to be hours. A fraction that has units that represent miles in the numerator and hours in the denominator are going to give me miles per hour. Since the numerator represents the difference of the y's of the points I create need to be miles. Since the denominator in my slope or my average rate of change needs to be hours and the denominator is x's, the x are going to be hours. So I'm going to create points. The x's are going to be times in hours, and the y coordinates are going to be the distance in miles. I tried to do something more cutesy here, but I kind of like this just fine. The units tell me what the y's are. The y's are the first unit that's mentioned. The x's are the second unit that's mentioned, and that's tried what I do here. The hours are mentioned second, so it goes in the denominator. The units, hours need to be the x's. The first unit mentioned is miles. It goes in the numerator. It has to go first. So I need to create 2 points. The time is going to be in hours. That's going to be the x's. And the y's are going to be some odometer reading in miles. So I'm just taking, at 10 a.m., the car's odometer is 10,300 miles. I created a point at 10 for 10 o'clock in hours, and then it's 10,300 miles. And then I did another at noon, which is 12. The odometer is 10,420 miles. And now I'm going to find the average rate of change between those 2 points. Subtract the y's in the numerator, the y of 10,420 minus the y of 10,300, divided by the x of 12 minus the x of 10. For time, this gives me 2 hours, because between 10 o'clock and 12 o'clock, that's 2 hours. And for the distance, that's 120 miles to go from 10,300 to 10,420 miles. This car went 120 miles in 2 hours. So its average rate of change is 60. And now the units, it's per unit of time. It's its average rate of change is 60 miles per hour. So when I try to say the average rate of change is how much the function changes per unit, the unit is hours, and it's changing at 60 miles per 1 hour time unit. This is what this is trying to say in its really wretched way. But this is an average rate of change without a function attacking on words. Anytime I have a word problem and I'm doing average rates of change, I usually should get units. And in this case, I told you what the units need to be, so I forced that to happen. So I typed up a bunch of stuff about this. So the average rate of change tells me this car's average speed over the interval, but it only tells us an average between 2 values of x. It doesn't give specific information at an instance. For that is, we have no idea how this function, what the speed was at any time. If I for this car that traveled at an average speed of 60 miles per hour over the 2 hours, I couldn't say at 10:42 what was the car's speed. I would have no idea. It could be more than 60 miles per hour. It could be less than 60 miles per hour. It could even be stopped. You know, maybe the driver was driving at 100 miles per hour for 90 minutes and stopped for 30 minutes. So we can't tell by looking at the average speed what the speed was at any particular moment. It's just an average. And this is the link between algebra and the link between calculus. Algebra allows us to find the average rate of change over any time interval. But it can't tell you at a specific instance what the exact instantaneous rate of change is. This is a big deal. So this car, we have its average rate of change, but the average rate of change doesn't tell me what happens at any specific instant. That's just an average over a time interval. If I want to know exactly at 10:44 what the car's speed was, well, I'm going to need a lot more information than I've provided. But in order to find an exact rate of change, which would be called an instantaneous rate of change, I'm going to need calculus. If I want to know the car's speed at an exact moment, I need to find the instantaneous rate of change, the rate of change at an instant, as opposed to over an average length of time. This is the difference between algebra and calculus. An average rate of change, just the slope of the line that connects 2 points. Instantaneous rate of change, it's the slope of a line at a single point, and we need calculus to do it. And this is the tricky part of this section, but hopefully I make it not so tricky. So we get bunches of words in the beginning of chapter 1 that carry over through chapters 2, 3, and 4. So at the beginning, bad things happen. So for this car problem, where I said at 10 o'clock, its odometer reading was 10,300. And who knows if the car was stopped then or was driving then. What if I want to know its exact speed at 10 o'clock? Well, to get an exact speed, to get the exact, not the average rate of speed, to get the exact speed, what I essentially have to do, as opposed to an average speed, if I want to get how about the speed at exactly 10 o'clock, if I want to be able to look at the odometer and know what the speed is, well, to find speed, it's still miles over hours. What I essentially am going to do is I'm going to create 2 points that are so close to each other that I can call them 1 point. And that's going to be the tricky part. Tricky for me to explain, tricky to do for a little bit. But the instantaneous rate of change is the average rate of change over the interval. So it's really the average rate of change over this interval from 10 o'clock to 10 o'clock. Well, what if I tried to do this? If I tried to do the average rate of change over the interval from 10 o'clock to 10 o'clock, I do subtract the y's, subtract the x's, and I get 0 over 0. That's good because that's the indeterminate form. This means if I had an equation, maybe there's some sort of algebra. To get the exact speed at exactly 10 a.m., this is now called, instead of the average rate of change, it's called the instantaneous rate of change. Can never spell instantaneous. And to get this, I need limits. Back in section 1-2, when we got 0 over 0, the limit probably existed, but I needed to do algebra. That's kind of what's going on here. So the instantaneous rate of change for this car will be a formula that will allow me to find the speed exactly at 10:44 in the morning or at 11:12 in the morning. There's nowhere near enough information in the problem that I presented to find it as exact speed. It's too generic, but we're going to learn a strategy to find the exact speed given formulas at an instant. So this uptick from the difference between average rate of change and instantaneous rate of change, average rate of change is just that. It's over a time interval. What was your average change or your average speed when you're driving? Instantaneous rate of change is at that second, how fast is the car going, or specifically something more complicated, what is the slope of a tangent line? We'll get to that in a little bit. But let me just read through this a little bit. So the instantaneous rate of change is the average rate of change over 0 length of time. And you can't calculate it with algebra because you have equal x coordinates. The denominator in the computation would get 0, which is undefined. So we're going to need calculus to do and limits to do instantaneous rate of change. Maybe I can scrub these pages and move on to this next page. And we start talking about the instantaneous rate of change. So the instantaneous rate of change is just the average change at a point. The instantaneous rate of change, this is the sneaky thing that we do. We create 2 points and we turn them into the same point. What I'm going to do is I'm going to create 1 point that has an x coordinate of whatever value I want, and another point that has an x coordinate of the original x coordinate plus some number, and then we're going to do algebra to let that number turn to 0. We're going to let some algebra, or actually calculus, to let this number go to 0, so that then the x coordinate of the second point is also going to be a. So what I'm trying to do is find an average rate of change at one single point, and I can't find the average rate of change just doing the same point twice because I get a 0 in the denominator. So I have to do some calculus trickery. I make a second point that doesn't have exactly the same x coordinate as the first point, and then I do limit calculus and then change the x coordinate of the first point to match the x coordinate of the second point. To make the x coordinates match, I change this h to 0. That's still more complicated than we need to get, but let's keep going and see what we can get. So to find the instantaneous rate of change, we want these 2 points to have the same x value of a. All we need to do is make that h be equal to 0, and we're going to use calculus. We're going to take the limit as h goes to 0, which is going to create this point and this point having exactly the same a's, and that's good. Then I'm going to find the average rate of change at a single point, and that becomes called the instantaneous rate of change. So the instantaneous rate of change is simply the average rate of change at a single point, because we're going to go from the point that has an x value of a to a point that has an x value of a plus h, and do calculus to make that h go 0, and then we're going to make the second point also have an x coordinate of a. So we're finding the average rate of change between 2 points that have the same x value, what I generally couldn't do, because when you subtract the identical x's, you'd get a 0 in the denominator, which is undefined. So let me put this ugly notation. This is on steroids, the notation that we did before. The instantaneous rate of change, that's the average rate of change not between 2 points, but the average rate of change at a single point, which is called the instantaneous rate of change. It's the slope of the line that connects the 2 points. One point has an x coordinate of a. The second point has an x coordinate of a plus h. And then I do trickery to make the h go to 0. And then essentially I'm finding the average rate of change at a single point. That's what the instantaneous rate of change is. It's the average rate of change at a single point. And when it's at a single point, it becomes the instantaneous rate of change. The average rate of change for my time interval gave me an average speed of 60 miles per hour with a formula for the distance the car is traveling. And this formula here for instantaneous rate of change, I could find the car's exact speed or its instantaneous rate of change at an instant, and then we're going to eventually do that. So the instantaneous rate of change is a measure of the slope between 2 points, the points that have x coordinates of a and a plus h, and y coordinates of f evaluated at a and f evaluated at a plus h. In the numerator, I'm subtracting the y's, the f of a plus h minus f of a. In the denominator, I'm subtracting the x's, a plus h minus a. And in the denominator, a plus h minus a, the a's cancel and I just get h. This is the power formula that we're probably going to use more often to find an instantaneous rate of change, which is essentially just the average rate of change at a point. This is heady stuff. The algebra is way less complicated than the theory, but you got to know some of the theory. At least I have to teach some of the theory. I could, I can drive my car without really knowing how it works. I can do calculus without really understanding the theory. This is a theory. Eventually, we'll get into the applications, and if you don't perfectly understand the theory, it's not going to kill you. It's not going to keep you from doing well in our class. So this semester, we're going to use the word derivative a bunch. And the terms instantaneous rate of change and derivatives have the same definitions and they're interchangeable. So if I say find the value of a derivative of a function when x equals to a, that's the same as saying find the instantaneous rate of the change of the function when x equals to a. This is a little heady right now for where we're at. We haven't done enough for this to make a lot of sense, but I feel obliged to write it down and say it because eventually I'll try to connect to it. So the formula for the average rate of change is the same as the formula for a derivative. If you look at this sheet right here, the instantaneous rate of change at a point and the derivative, these are the same things. Instantaneous rate of change and derivatives are interchangeable words. They're the average rate of change at a single point, and we do it using limits. If I'm given a function that's called f of x, this notation, when I put a little symbol like that, I guess I call it a prime symbol. This is called the derivative symbol, which is a symbol for the instantaneous rate of change, or the average rate of change at a point. So that little prime, we call that derivative notation. And if I see this, I will know that this is the instantaneous rate of change at a point. So we're going to use the symbol f prime of a to represent the derivative at a value. And the derivative is just the slope of the line that connects the same 2 points. One has an x-coordinate of a, the other has an x-coordinate of a plus h. The y's are shown using proper function notation. I want the points to have the same, a single x value, and I do that by changing the h to 0. When I change the h to 0, I get 2 points that have the same a value. So let's do an actual problem and get out of the theory into the computations. And the computations are a little grungy, but we can do them. So if I want to find the instantaneous rate of change at a given value, I need to create 2 points. One of them has the x-coordinate of the given value. The other has an x-coordinate of the given x value plus h. So let me show you. I want to find the instantaneous rate of change for this function at x equal to 2. To do an instantaneous rate of change as opposed to an average rate of change, I need 2 points. One point is 2, comma, the function evaluated at 2. And the second point's the ugly one. It's x equal 2 plus h, y equals the function evaluated at 2 plus h. So down here I do the algebra. To get the y-coordinate of my first point, I take each one of these x's and I plug in 2. So I plug in 2 for that x and get f of 2. Plug in 2 for that x and get 3 times 2 squared. Plug in 2 for that x and get minus 5 times 2 plus 4. Apparently on my calculator this comes out to be 6. So one of the points that I'm going to use to find the instantaneous rate of change is the point 26. That's the easy point. To get the second point, I need to take each x in my function and change it to 2 plus h. So to do f of 2 plus h, that's the x-coordinate of the second point. To get y's, I take the function that's provided to me and I change all the x's in the function to that x, in this case 2 plus h. Now this is ugly math. To do this math, I'm going to do the exponent first. To figure out the y-coordinate of the second point, I'm going to work on this piece first, and I'm going to do the exponent by foiling. I'm going to go 2 times 2, which is 4, 2 times h, which is plus 2h, h times 2, which is plus 2h, and h times h, which is plus h squared. I'm going to write this in a nice order. I'm going to write the h squared first. I'm going to add the 2h and 2h and get 4h. And I'm going to write the 4 second, the 4 last. So as I'm going to find the y-coordinate of the second point, the algebra that's necessary is plugging in 2 plus h in for my x's, and now I do the math. So the math here is going to give me 3h squared plus 12h plus 12 minus 10 minus 5h plus 4. There's a little bit of like terms right here. The 12 minus 10 and plus 4 can be combined, and the 12h and the 5h can be combined. The 3h squared can't be combined with anything, but 12h minus 5h is plus 7h, and 12 minus 10 plus 4 is equal to plus 6. So the y-coordinate of my second point is 3h squared plus 7h plus 6. So now I have 2 points. I have the point 2, 6 and the point 2 plus h, comma, 3h squared plus 7h plus 6. The instantaneous rate of change is just the slope of the line between those 2 points with with the limit as h goes to 0. So now let me find that instantaneous rate of change by simply finding the slope, and I'm going to say the instantaneous rate of change, and this is the formula for instantaneous rate of change, the function name with a little prime. The instantaneous rate of change, or the derivative, when x equals to 2, is the limit as h goes to 0, and then in the numerator, I'm going to put the y-coordinate of the first point, 3h squared plus 7h plus 6, minus the y-coordinate of the second point, minus 6, and then I could subtract the x's in the denominator, or I can just write h in the denominator. I could write x-coordinate of the second point minus x-coordinate of the first point. The denominator is always going to come out to h. So now I'm going to cancel the 6's in the numerator, the 2's in the denominator. So the instantaneous rate of change, or the derivative, when x equal to 2, can be found by using 3h squared plus 7h over h. I forgot the limit as h goes to 0, which is a huge deal. I need to make the points the same point, so I need to have that limit on there. In the numerator, I can factor out an h and get f. Well, here it is right here. When I factor out an h, I get the limit as h goes to 0 of h times 3h plus 7 over h. I could cancel the h's and plug in 0 for h and get 3 times 0 plus 7, which is 7. So the instantaneous rate of change when x equal to 2 is 7, or the derivative of the function when x equals 2 is 7. These both say the same thing. So the slope of the line that connects the point 2, 6 to the point 2 plus h, 3h squared plus 7h plus 6 is 7. And this is probably a time to take a break because we're at 33 minutes right now. And I have a whole nother example to do, and I don't want to do it, and because it's going to take like 8 minutes, I don't want to do it in this video. So let me pause the video and make a